The following figure depicts the upper half of a boiler with the piping system conveying steam to the point of use. This piping system represents a typical configuration of a steam reducing station, including a control valve and a condensate trap set. These will be discussed in detail in a later section. Now, if the water level inside the boiler were not carefully controlled, the consequences could be catastrophic. If the water level drops too low and the boiler tubes are exposed, the boiler tubes could overheat and fail, causing an explosion. If, however, the water level becomes too high, as highlighted here, water could enter the steam system and upset the downstream process. The result would be wet steam. For this reason, automatic level controls are used. The following figures depict two examples of level control system used for a steam boiler. The left-hand system is an on-off control. The right-hand system is a continuing modulating control. Boiler controls and control theory will be explained in a later section. For now, keep in mind, to comply with legal requirements, level control systems also incorporate alarm functions which will operate to shut down the boiler and alert attention if there is a problem with the water level. A common method of level control is to use probes or sensors, as seen here, which sense the level of water in the boiler. At a certain level, a controller will send a signal to a control valve or a feed pump which will operate to restore the water level, switching off when a predetermined level is reached. The probe will incorporate levels at which the pump is switched on and off, and at which low or high level alarms are activated. A typical example is now shown on screen for the purpose of illustration. Now, it is important to note here that for steam boiler safe operation, it is a legal requirement in most countries to have two independent low-level alarm systems. Take a look at the following figure. It depicts a steam boiler and various process equipment. These equipment use steam as the heating medium. Now, once steam is generated in the boiler, it flows through the piping network to provide the necessary heat energy for the downstream plant items. We'll call P boiler the pressure of steam exiting the boiler. When steam is used as a heat transfer fluid, its temperature decreases. This drop in temperature condenses the steam and gives condensate as seen here. When steam condenses, its volume is dramatically reduced, which results in a localized reduction in pressure as depicted here. This pressure drop through the system creates the flow of steam through the piping system. Now, the steam generated in the boiler must be conveyed through the piping system to the point where its heat energy is required. Initially, and as seen here, there will be one or more main pipes or steam mains which carry steam from the boiler in the general direction of the steam using plant. Then, smaller branch pipes can then distribute the steam to the individual pieces of equipment. It is important to keep in mind here that steam at high pressure occupies a lower volume than at atmospheric pressure. The higher the pressure, the smaller the diameter of the piping system required for distribution of a given mass of steam. This will be explained in further detail in the sizing section of the course.